So now we're going to turn to projectile motion, and this is essentially two-dimensional motion. Now, we've been drawing two-dimensional diagrams to represent linear motion because one of our dimensions has been used to represent time. In this case, both dimensions are representing some spatial quantity, and we could call one the x direction and one the y direction. So the basic setup for projectile motion looks like this. So I'll draw a picture. So say we have a flat surface here, and we launch a rocket, or, well, rocket would be a bad idea, I guess, in this case, because it's not a simple projectile. It's ejecting stuff. It's not just launched. So let's say like a cannonball or something. And I'm not going to draw the cannon. What I'm going to do is I'm just going to draw the trajectory. So this is what's called a trajectory. So this is the path that this follows through space. Now, after we draw this picture, we could add some more details. I could draw a vertical axis here, and I could call this the y direction. I could call this the x direction. And so this projectile is going to start out going up like this. Now, notice x and y, like I said, these are both spatial directions here. There isn't time involved. The way time would be involved in this is you would actually see the projectile go like this on this given graph here. But neither the x nor the y represents time. They both represent space in different ways. And so we're going to have a launch angle. Now what the launch angle is the angle at which this starts out going. So I could draw a line that goes like this. And so this would be if there was no influence of gravity to pull the projectile back down to make it hit the ground. And so this launch angle here, I will call theta. And then so what happens is the particle, cannonball, whatever it is, it starts out at this angle, but then gravity is pulling it downward, and so eventually it will hit a maximum height. So this would be the max height here. And then it will start to fall, and it will fall, and it will land here. Now, if we ignore wind resistance, which is a pretty good approximation for something heavy like a cannonball, then this will actually be what's called a parabolic trajectory. That's in the approximation that gravity is constant and all this kind of thing. If you had wind resistance, then it would look a little bit different. You may have seen a good example of this is like a kickoff, like if you've watched like a football or soccer, depending on what you call it, a match. So you have a surface like this, and the ball, gets kicked like this, and it goes here, and then it will come down kind of like that. And this is because there's wind resistance. And that's because a ball is not, an inflated ball is not like a cannonball. It's much lighter. And so the force of wind resistance, or drag, as you could call it, is much more significant in this case. And the book has a little picture in it. I forget what page it's on, but it has one sort of what the trajectory would be, and then it has another what the trajectory is when you add in wind resistance. But in this case, we're kind of just ignoring that. Now, there are variables associated with this, and because there are two different spatial directions, the x direction and the y direction, there are essentially twice as many variables going on. And the way you always analyze projectile motion is you think about the motion in the x direction as independent of the motion in the y direction. So you take a two-dimensional problem, so 2D problem, and you convert this to two one-dimensional problems. And each of these one-dimensional problems are precisely linear motion problems like what we've been doing, involving constant acceleration. And so when we make the approximations that there's no wind resistance and stuff like this, what we get is the situation we end up with is the projectile, the cannonball or whatever it is. So it moves at a constant velocity in the x direction, and it accelerates downward due to gravity in the y direction. Now, this is one of those cases in which the acceleration and the velocity can be in opposite directions. You remember the problem we had with the car where it goes off the interstate onto the off-ramp and it's still moving forward, that's its velocity, but its acceleration is backward because it's slowing down. I was telling you how you can tell the acceleration because the seatbelt is pushing back on you. Well, here, the projectile starts off in the y direction, it's moving upward. That's the y motion, starts off upward, but the acceleration's downward. And so this whole time up to where it gets to this maximum height here, the velocity and the acceleration are in opposite directions. The velocity's up that whole time and the acceleration's down that whole time. So this is kind of a prototypical example of how that works. Now let's talk about the equations and the variables in detail. Now I have to do something different than what the book is doing here, and the reason why is because the book is using this variable x to mean two different things, and that's just not going to cut it. So book uses x for two different things in the same equation. That's just a big no-no. You can't do that. So two different things in the same equation. Now, what these two things are is, so it has it has an equation something like x0 x, and then it has x0 y. And so for the book, this means this x0 x means this is initial x position, and the x0 y is the initial y position. So the two different things it means, now notice it's using x to mean position in general, in this case position or displacement if you want to say it that way, is a vector that has two components, but then it's going and calling the first component the x component. So this x means a different thing from what this x means, because this x means the position or the displacement vector, and then this x means the x component of the displacement vector, whereas this one means again the displacement vector, and this one means the y component of the displacement vector, and that just won't cut it. That's too confusing. So what I'm doing instead is I'm not calling the whole position vector a single letter, x, for example, like what the book does. I'm distinguishing the x position from the y position. So x0 just means the initial x position. Y0 means the initial y position, which are both 0 in this context. You see, this is the origin, x equals 0, y equals 0. And so that's what these two equations are saying, that the initial x position is 0 and the initial y position is 0. So in that case, we're making our notation a little bit different than what the book is doing. Now, what I'm doing for the velocity is I'm calling the two components of the velocity Vx and Vy. And then what the 0 is that's the initial value of the, in this case, the x component of the velocity, and here's the initial value of the y component of the velocity. So these two equations here, Vx0 equals v cosine theta, Vy0 equals v sine theta. What's the v? Well, v is the initial speed. That's the initial magnitude of the velocity when this thing is launched. So I'm going to erase this picture and I'm going to draw a little bit bigger without all the commentary on here so that you can see why those two trigonometric equations come in here. So let's draw our coordinate system larger. Now I'm going to launch this cannonball or whatever it is in this direction. Now of course it's not going to stay going in that direction because of gravity. It's going to, well, it's not very well drawn. Let me try again and see if I can be a little bit more accurate. So it's not going to stay going in that direction. It's going to eventually be pulled down by gravity. But we're just going to look, I'm trying to explain these equations, these middle equations here, the initial x component of the velocity, the initial y component of the velocity. So what I can do is I can take this arrow which points in the direction of the launch. So this is the launch direction. And I can turn this into a right triangle by dropping a vertical line down here. So this is a right angle here. And you notice that if the length of this arrow here is v, so the v, so why am I calling that v? So this is the size or magnitude of initial velocity. That's how fast it starts out going. That's the muzzle velocity. If you're talking about like shooting something out of a gun, that's v, and so that's represented by this length here. Well, you remember your trig. That means this length here has to be v cosine theta, and this length here has to be, erase this, v sine theta. So now this length here is exactly the x component, so I'm going to call this the x component of the velocity, and it's the initial value of that. So I'm going to put a v, an x, and a 0 here. And this one I'm going to call, this, well, what you would expect. Initial y component velocity with a 0. That's what it's starting out at. So that's what those equations mean. And then I have equations which are talking about acceleration. And that's this ax equals 0, ay equals minus 10 meters per second squared. Notice I don't have an ax 0, I just have an ax and an ay. And the reason why is because I'm assuming constant acceleration like we have throughout this whole chapter so far. So that's why I don't have to specify an initial one. See, the velocities will change. As gravity pulls it down, the velocities will change. The acceleration doesn't change. Now what the ax equals 0 says, so ax equals 0, this says velocity stays constant in the x direction. And then ay equals minus 10. Where does that come from? Well, that's the force due to gravity, and you may be used to minus 9.81. So this is meters per second squared. This is sort of the more precise one. So what this says, what this equation says, that y velocity changes due to gravity. And we put the minus sign in there because it's accelerating down. And we agree that the upward directions are positive directions. So when we want to talk about going down, we have to have a minus sign there. So that's what this says. Now, let's do a problem, because this has all been somewhat, well, very theoretical. So let's say launch a cannonball at 100 meters per second at an angle of 30 degrees. Well, let's say 60 degrees instead. That's a little, well, no, 30 degrees. This will be easier to draw. So 30 degrees. And if you like radians, this is pi over 6 radians. How far does it go? So what the picture would look like is I'm going to start off, so this is 30 degrees, or pi over 6 radians, and then what's going to happen is it's going to go like that, and eventually it's going to hit over here. And it's this distance that we care about. That's the how far. So this is how far. So this, I could call this x. Well, how can we solve this? You remember, so to solve, and I'm going to have to erase this because I'm not going to have room to do it all, but to solve, recall the x velocity is constant. So whatever the x velocity started out as, whatever the component of the velocity in the x direction started out as, it's going to keep that same velocity the whole time until it hits. So what that tells you is that we can find the distance by just finding out the time. So once we recall the x velocity is constant, so solve for time. I named the x velocity Vx, so I'll call it here Vx is constant. That's the velocity, not the nerve agent. So recall x velocity Vx is constant. Solve for time, t, then the final distance there, x, is just going to be that velocity times the time. So how do we solve for t? Well, to solve for t, we're going to have to use, so what is t? T is the time it takes to go up to the highest height and then fall back down and hit there. So we have to figure out how long it takes to go up and then come down. Now that involves the motion in the y direction, and I told you to solve problems like this, we split them into two problems. This is the x part, and once we get the y part, we can plug it into the x part and get our answer. But now we have to analyze the y part, and that's a little bit more complicated. So let me erase this just so I have room to draw. And I'm going to redraw the picture here. So we had a 30-degree angle here. And then this goes and it comes down and hits over here. Now what we're going to care about is we're going to care about the y component of that velocity. And we're going to have to find out how long it takes for it to go up and come down. So, what do we need? Well, we need the Vy, and we need the initial value of it when it's launched. And this So I gave you that equation here. So we have Vy equals, it's this initial value of the velocity times the sine of the angle. Now, I told you the initial value of the velocity, that was the launch velocity, so this was 100. I'm not going to put the units in now. We'll fudge them at the end. And then this is sine 30 degrees. 30 degrees, the sine of 30 is 1/2. So this is 100 times 1/2. So this is 50 meters per second. So the time to the top, so that's where it reaches up here. Well, it starts out at going upwards at 50 meters per second. It's accelerating constantly downwards at -10 meters per second. It's going to hit the top. What the top means is that the y velocity is 0. That's where it comes to a stop in the y direction and then starts going back down. So the time to the top is going to be 5 seconds because it's accelerating constantly downward at -10 meters per second squared, and so it takes that long to cancel out the upward initial velocity of 50 meters per second. So time to the top is 5 seconds. That's the time here. Well, we need twice that time because it's going to hit over here. So, and this part is going to be symmetrical. This part is going to be symmetrical to that part here. So my time to land is 10 seconds. Now you remember I said x, the x distance, that's just the x velocity, which is constant, times the time. What is that x velocity? Well, it's constant, and so this is the same as what the initial velocity is. That's Vx0 times time. What's Vx0? Well, I gave you that equation. That's the initial speed times cosine theta. And then this is times the time, all still written in variables. And now we can plug in what those values are. The V was 100. The cosine theta, what's cosine of 30 degrees? It's square root of 3/2. And that's like 0.866 or something like that. So that's 100 square root of 3/2. The time, we said this was 10 seconds. So this is going to come out to be 10 times 100 times square root of 3/2. So this is 1,000 times square root of 3/2. So this comes out to 500 square roots of 3. And this is about 866 meters or something, if I remembered my decimals correctly. You could work this out if you want to use your calculator or something. So that's how these problems work, and that's sort of a typical problem in this context. Now I wanted to say one more thing, and that is that the book gives you a formula for figuring out what the highest height, what the maximum height of the projectile is. And what the book suggests is that you should rearrange this formula here, this max height. And so here they're calling the max height H. I would maybe call that Y or something, so we're measuring that in the Y direction. So this is rearrange this V equals square root of 2GH. But you would have to remember that formula, V equals square root of 2GH. If you want to, you can do something else. And so I say this is better simply because it's easier to remember, even though maybe it takes a little bit more writing out. Notice that this is using the same idea I used to tell you that it takes 5 seconds in that last problem for the projectile to get to the top to its maximum height. So this was the initial velocity going up. I could really put Vy here. That would be, I guess I should put, well, I'll write it different here. So this is alternative. there I was abbreviating by just writing v. But what I could do is I could say the time to reach the top t is the initial y. I guess I wrote it in the other order. I wrote vy0 divided by g. Now, and so remember what this was before. This was 50 meters per second, and then this was divided by 10. There's a sign in there. Here I'm calling g positive and saying that acceleration is minus g or whatever. You're not going to get a negative time, so this is 5 seconds. Anyhow, so once you have that, then you could use, so then you remember from previous lecture, the way we wrote this formula there was x minus x0 equals v0 t plus 1/2 a t squared. So we're using this kind of formula, but we're not using x's anymore. We're changing the names of the variables because we're moving in the y direction. And so the distance we're interested in here would be that distance h. So this is what this really is. This is y minus y0 is what we're going to care about. And then this is going to be vy0 t plus. Now, the acceleration due to gravity here, so this is minus 1/2 g t squared. And then we can plug this in. So this thing here is h. This is what we want. And so this is, I plug in for t here, and so I'm going to get this vy0 squared. Vy0 squared over g. And then this is going to be minus 1/2, the same thing, because this is going to be g, and then this is going to be v y0. I get the sense that you're not going to like this very much. vy0 over g squared. And so this, you can work this out. This becomes this becomes just vy0, 1/2 vy0 over g. And that's the same as what you would get here, because if I took this and I square both sides, I get v squared, and of course this really means vy0 squared. And over here I get equals 2gh, and I rearrange this and I get vy0 squared over 2 g, which is the same as that, equals h. So that's the same formula as what this is. Anyway, I suspect that I shouldn't have spent 5 minutes on that, but you'll forgive me. You can take it or leave it. All right, so the last thing talked about is center of mass, and this is something that is just discussed here very briefly in a purely qualitative way. It's not, really putting numbers into it. So this is center of mass. And it's easiest to illustrate this. So I have here a hammer. I have here a hammer, and so that the head of the hammer is made of iron or something. And so you see there's this whole handle of the hammer which weighs as much as what this head part here. So the center, so this would be, it's going to rotate around a point that's very close to the head. Now I'm going to spin this hammer in the air, and I'm not going to be able to catch it, so it will drop. But what you'll see is that the handle will go around very fast, and the head will stay in essentially the same place. And that's telling you the center of mass. See, when it's moving, you could think of the whole thing as a projectile, and all that complicated motion you could think of as just being that center of mass moving along, and then the rest of the body just kind of rotating around it. So if I spin this, see, and then it hits the ground, if I spin it, you see it rotating around the center of mass there. So you can simplify motion problems by thinking of complicated objects as single points at their centers of mass. So if I took that hammer and I threw it a long way, and you could watch the motion of that hammer and you think, well, that's really complicated because it's rotating and stuff. But you could treat that hammer, that whole thing, as a projectile, like those projectile problems that we were doing before, like a cannonball, like a single point. You could treat that entire hammer as just a single point moving at its center of mass. And what you would see is you would see the center of mass moving along in this nice, predictable parabolic trajectory. And the hammer itself would be rotating in some kind of, funny way. Like, here it's going like this, and then maybe, it's going like this. And so the thing is spinning around in a very complicated looking way. But you can ignore that. You can just think about the center of mass moving, and then whatever the hammer does around that center of mass, that's not so important. One more example of this is the solar system. So I'll say, e.g., the sun, and we'll just say Jupiter since it's bigger than all the other planets. So you usually think of Jupiter as rotating around the sun. Well, it doesn't. Both Jupiter and the sun rotate together around their common center of mass. So sun and Jupiter, they rotate around their common center of mass. And so the way the picture looks here is you have the sun here, and then you have Jupiter over here. And so now it turns out the sun is much, much larger than Jupiter, although Jupiter is much, much larger than the Earth. It's like 300 times as large as the Earth. And so the way it ends up looking is Jupiter goes in a very large circular, or actually more elliptical, close to elliptical orbit here, whereas the sun, so the center of the mass of these two together is very close to the sun. So this is the center of mass, but it's actually outside the surface of the sun. And so what you see the sun is going in a very small orbit around its center of mass. This is wildly exaggerated. I mean, if I do the sun like this, then the center of mass would be sort of like just outside the sun. So you just barely see the sun kind of wobbling around like this. But the distances, the astronomical distances, are so great that it looks, for all intents and purposes, as if the sun just stays there and then Jupiter orbits around it because the sun's so much bigger. But what's really happening is they're both orbiting around the common center of mass. And of course, this ignores the gravitational attraction of the other planets and the other stars in the galaxy and things like that. But for any sort of system, you can think about the motion of it as being around its center of mass. And it's often a very simplifying sort of idea, like with the hammer, that you can ignore most of the motion that's going on and just think about the motion of the center of mass.